Okay, thanks everyone. I'm going to talk about using umbrage and task communications to handle complex problems in CO2 storage. So I'll just introduce the issue here. We're trying to predict what's going to happen to CO2 in underground storage sites long into the future and the way in which the rock structure determines this. The company I work for, OpenGoSim, support an open source reservoir simulation code which is highly optimized for CO2 storage. Being open source is quite a minority interest in the reservoir simulation game. Most of the main players, Schlumberger's Eclipse, for example, are proprietary codes. Now, these are major simulation tasks. We're doing big structures and we're running them for very long periods of time. And we almost always run in the cloud, typically on 500 processes, using MPI coupled high performance computing. And the core of any model is the flow calculation within the porous rock of the reservoir. So I'll give an example. This is a field called Smehea. It's a big area, several tens of kilometers of porous rock off the Norwegian coast. And when I started on this, it was a hypothetical project. Now it's a real project and likely to happen. And the idea is that we're going to inject 4 million tons a year of carbon dioxide from, let's say, 2022 for 25 years. And our task is to determine what happens to that CO2. So here's the results of a typical simulation. We start injecting, and 13 years after we start, the CO2 starts to appear at the top of the porous region. There'll be some sort of non-porous region sealing above this. We go forward 300 years, and the CO2 is now at the top, and you can see it's migrated to the crest of a reservoir that's beginning to pool up here. We go forward 20,000 years, the injection stopped, and what you can see is the CO2 started to dissolve. CO2 is soluble in brine, it falls into the brine, is heavier than the original brine, falls down into the reservoir, and possibly in the long term, it will mineralize with the metallic ions in the reservoir to form salts. So this is clearly quite a complex problem, and it's really multi-physics as well. So I've mentioned the brine. We're worried about brine precipitation. We have temperature effects. We have the geomechanics of the reservoir moving under the stress of the injection. We have the geochemistry of the long-term mineralization. And this whole thing ought to be done really with uncertainty quantification over an ensemble of runs. I was very excited by what Delphine wrote today, which was talking about today, exactly what we're after, doing a lot of runs and then a statistical analysis to see what the risks and variability are. As I mentioned, 100-kilometer storage regions, and often what appear to be independent regions are actually coupled by underlying aquifers and thousands of year timescales. Now, when you inject CO2, you hope never to see it again. So the question is, how do we know what's going on? And so we have to try and monitor it, either with time-dependent seismic or even gravity anomaly detection. So part of the job of what the simulator does is to produce a synthetic monitoring result to compare with a real monitoring result. And finally, economics is a big deal. If you're in the CO2 business, you're in the waste disposal business, and that's not got a lot of money in it historically. And so the costs of injection and monitoring have to be compared against the storage cost when you undertake to do this disposal. So one thing you don't want to do, I think we can say with some confidence, is put all this into one vast mega program. So we have to split it up in some way. Now, we all know that to handle complex systems, the standard approach is modularity, interfaces, and coupling well-established solutions. In the reservoir simulation business, there's at least been a well-defined common file interface based on what Eclipse did 30 odd years ago. And we're now looking at runtime interfaces, sockets. OpenEclipse again is a proprietary solution produced by Schlumberger. Rex is another proprietary solution owned by Aspen Tech. And now we're looking at umbrage. And the real idea is we do a series of times, we do a calculation or data exchange with a geomechanical or well modeling solution. We update the main model and we move on to the next time. And for flow simulation, it's important that we don't just need the value of the rate produced by that well. We'd like to know the derivative of it as well, because we're going to do a fully implicit coupled solution. So our aim here is to have a way of coupling pFlowtran OGS to a range of other codes, and there may be half a dozen of these going into the future. And the way we've done this is to define a little protocol we call OPX, which can run over systems like Umbridge, and now does. So OPX is rather similar in some ways to OpenEclipse. The basis is a simple application-neutral data packet, and that data packet has a mnemonic, it has a type, and it has a number of items, and it can carry a payload. So an example might be, here's an array of 401,000 pressure values, and they're all reals. The basic approach is half duplex, so it's a dialogue. We do a simulation step, and basically the client waits. We get to the simulation step, we have the pressures, we send them to the mechanical package potentially, and then we have a dialogue where the server and the client can ask questions of each other and return values. So that's a bit abstract. So here's what happens in a case I'm going to look at in a minute. We start the reservoir simulator as a server. We then start the geomodel as a client. The geomodel goes into a waiting mode. The simulation takes a number of steps. When it reaches a point where it's ready to do a dialogue, it sends a start dialogue to the client. The client requests the pressures because this particular client needs pressures. The simulator sends the pressures. And it's worth saying that these are highly parallel MPI programs, but the actual sending is done by process 0. So in fact, in terms of coding this, the biggest amount of effort is actually collating the results from process 0. The geomodel now has the pressures, it does the stress calculations, it finds the effects on the pore volumes and the transmissibilities, and it sends them back with a mnemonic starting S pore volume mult, S tram mult. The simulator said, great, I'll update the transmissibilities and continue on my next step, send finished dialogue, and the geomodel goes back into waiting mode. And this pattern can be used for a lot of possible things, including the well models. In the case of the well models, it's a little bit more subtle how much dialogue you do. You might say how many wells are there, how many inject CO2, what's the name of the first one that injects CO2, what's its pressure, and then I'll hand you back the flow rate. So to demonstrate this, I did a little example. This is actually a cross-section through a rather generic CO2 storage site. I'm using pFlowtran OGS, and I wrote a little toy geomechanical package. And usually the model goes right from the seabed down to 1,300 meters, and I put a sealing layer in layer 50, and I've added a fairly realistic heterogeneity to the permeability distribution. I mean, this distribution is unknown, of course, which is where the uncertainty comes in. But in this case, it's just a random log K variation. I'm going to inject 1 million tons of CO2 into the lower region of formation, below the sealing layer. And the geomodel is just going to scan the pressures and say, look, if I see more than 10 bars across that seal, I'm going to let the seal break. And so I started the injection in 2030. I ran this as it happens on Windows using a 4-core simulation and 1-core geomodel. And we can do Linux and Windows support. So I'm going to track the carbon dioxide fractional gas saturation. So here we see the situation 5 years after we started. The CO2 is now rising in a plume. It's just hit the seal, and you can see it's starting to pull up and accumulate. So here we are 40 years in. We've now got 8 million tons of CO2. It's a kind of inverted lake up against that top seal. Okay, utter disaster. We've gone and broken the seal. We put too much pressure in. You can see the CO2 rising through the break in the seal. And we'll go on 75 years and we can see this is a point at which the CO2 actually gets to the subsurface. So this isn't a complete disaster. A lot of CO2 is actually still trapped, but this CO2 in the red region will continue to leak for some time. And ideally, we'd prefer not to do this. So we'd reduce the pressure rate or maybe stop when a certain pressure is obtained in our geological modeling and take it more easy. So in terms of how Umbridge fits in, OPX can run with either sockets or Umbridge as the driver. We started with sockets and now we're moving to Umbridge. We had to slightly modify a few bits of Umbridge, but we'll feed that back to the group. Umbridge is open source and we found it extremely easy to work with, and the clarity of the code means we've had no problems. The simulator, pFlowtran OGS, is actually written in Finode Fortran, So you can add another language to the list of things that interface to Unbridge. The GeoModel C++, and we have Fortran and C++ interfaces around the OPX code, which is fairly trivial. OPX is a Fortran binding around a C binding around a static class, around an allocated class which holds the persistent state of the input and output. So if I could summarize, we want to couple our simulator to a lot of other applications, some of which may be proprietary. The first is geomechanics, the next will probably be a well model, and after that comes a multiple realization handler. The nice thing about the data packets is they're self-documenting. So you can get a stream of packets, read the header and think, I don't care about this, pressures are no interest to me, I'm waiting for concentrations, and just ask for another package. And it's not tied to any particular pair of applications, and we can release this to people who don't want to send us their source code. OPX is initially built over sockets, but sockets are a bit raw and close to the system. There's no way in which Amazon Web Services is going to let us open a socket on one of their servers. Unbridge offers big advantages in that we can go to the cloud, which we want to do, and we're looking forward with some interest at how fast the shared memory transfer is on one machine. So we're moving to that, and we'll probably become purely an Unbridge protocol fairly shortly. So I hope that's of interest, and with that, I'll stop sharing.